Hello everyone, thank you for joining us this month. Today we are pleased to have Mesut from Hazelcast. His talk is on cache-first cloud-native microservices. He is a tech lead at Hazelcast and a self-proclaimed Java developer. He leads an interesting travel life. He has lived in Turkey, Belgium, and now the States. The agenda for today is an introduction to Hazelcast, the company, and the technology, an overview of caching patterns, what those patterns look like in Kubernetes, and finally, a review of day 2 operations. Mesut, thank you for joining us today.
So Hazelcast is actually open source company. Hazelcast IMDG, in-memory data grid, and Hazelcast Jet, they are both Apache 2 license, fully hosted on GitHub. So you can go for contribute. You can do whatever you want pretty much. Hazelcast IMDG is in-memory computing platform, and one of the main features are distributed caching. So you can use Hazelcast for distributed caching. Hazelcast Jet is a stream processing engine. Hazelcast Cloud is a hosted version of Hazelcast IMDG. So if you don't want to maintain Hazelcast cluster, you can just go create an account and start your cluster over there. And Management Center is managing and monitoring dashboard for Hazelcast. And it is free up to three member cluster. So if you have three member cluster, OSS member cluster, then you can use Management Center for free. You can check the career website. Hazelcast recently raised some money, so if you see any fit for you, then you can apply. And it's a remote-friendly company, so you can work remotely. So why distributed cache? That's the in this presentation, I'm going to focus mostly on distributed cache stuff. So why distributed cache? There are two keywords over here. One is cache, and the other one is distributed. So cache is normally, as you see on the presentation, is faster. Memory is faster than storage. So if in data-intensive applications, mostly you store your data somewhere, you query it, you do batch processing, stream processing, etc. But you need to have cache also if you want to have performance improvement and some data redundancy. So in that sense, cache is important based on your requirements. So in some architectures, they just put more hardware to solve that kind of problem, but you can use cache for performance improvement and fast access to data. Distributed stuff is also important because, as you know, everyone is just talking about moving from Monolith to microservices, and not every application now is just a one giant application. So each component, they have to talk to each other on the network. So the solution that you choose as a distributed caching has to be, distributed, or it's network aware. So in that sense, Hazelcast is a natural fit for cloud native deployments because as from day one, it's distributed. So its topology is not master slave topology. It is masterless. So whenever you just add or remove new Hazelcast nodes members, then they will join or leave the cluster. And afterwards, data is distributed, partitioned across the members. So that is why distributed cache. So one example here, there are several use cases you can use a caching solution in your architecture. One is read-through cache. So in read-through cache, I think you don't see the laser, but on the application, this can be a microservice. So you do map.get, some kind of lookup from Hazelcast cluster. If data is not there inside the cluster, then that means a cache miss. And Hazelcast cluster will get the data from data store, put into cache, and then return the value to the application. And in subsequent calls, you will receive data directly from Hazelcast cluster, which is much faster than reading from data store. So this is read-through cache. The other variations of those use cases, write-through cache or write-behind cache, where you can asynchronously write to the data store. And all these three, read-through, write-through, and write-behind cache, you just deal with Hazelcast API. You don't deal with the data store behind the cluster. There is another one, which is cache-aside, where you are normally responsible to check the cache and see if it is there. If it's cache miss, you directly go to your data store, fetch the data and put cache. So this is a cache as a side use case. That's another use case that you can use. In the map store, map loader, this read-through cache use case, you need to implement Hazelcast map store and map loader interfaces. We don't have off-the-shelf adapters for different data stores, so you need to implement based on your requirements. So it can be a relational database, no relational data, no SQL database, or you can even put into disk your data. So those are how you can use Hazelcast for your caching requirements. So in Hazelcast cluster, every member keeps a primary data and backup data. So on the top, you see that this partition 34, it says one comma carry actually on the top. So the primary data is key value pair is on the first member, and its backup is in another member. So this 34 is partition count actually. So Hazelcast by default, the distributed map by default with one backup count backups every data in another member. So why do we do that? We do that because if one member crashes, let's say that the one which is holding the backup, then primary will send the backup to another member. Okay, and if primary crashes, then the backup will be promoted as a primary, and then it will send the backup to another member. So this is a partitioning of the data, and this is how Hazelcast keeps the data in the cluster. Okay, so Hazelcast Kubernetes caching pattern. So I just explained Hazelcast and how what kind of use cases you can use in using Hazelcast. So how can you implement those in Kubernetes environment? We in the community, in open source community, in customers as well, we see different patterns that they use in Kubernetes environment. So I listed those on the slide. So embedded is one option. Sidecar this is famous Kubernetes sidecar. Everyone just hears all the time. Proxy cache and client server. So I'll go through them in the next slides. So this one is embedded. If I can just move this.
Click on left.
That's fine. Okay. So this is embedded. So this is a simplest Kubernetes cluster components that you can see. HTTP request comes in, it is terminated by Kubernetes service, which is probably a load balancer, and then it directs the request to a microservice. And in this picture, when microservice process data, each microservice can start its own Hazelcast member inside the process. It is a Java-only solution, JVM language-only solution, and it is very simple to use, because in caching architectures, you need to have a cache service somewhere, etc. But here you don't need to have a cache service separately. So each microservice will start its own member, and then each member will just form a cluster. The disadvantage of this pattern is that not everyone wants to keep their cache data together with microservice. And the other disadvantage is that if you increase the replica count, so scale out your microservices layer, then you will end up having lots of members too, which is not always good. Because Hazelcast is network intensive, so lots of network communication between the members. So this is, but if you know what you are doing, and if your architecture is simple, lots of people are using this pattern, and it just goes together with your microservice deployments. Yeah.
Does it compare after it splits it up and does whatever it does?
Does it what? Does it?
Well, you say it splits it up, and each one, your Spring Boot microservice, there is two different things. Are they doing that so they can compare them or just back it up?
They share the data, all the members, okay, and partition. It's not, yeah, that's a very good question because people are asking. Just over here, the Spring Boot microservice does not have to talk always to this member. As data is partitioned and Hazelcast client and members also is intelligent enough that the member knows where the data is. It directly goes to that member. So in this case, some lookups can end up over here from that microservice. But if you deploy in this architecture, as I said, the easiest part is that you don't have to have a separate cluster, and all those members will find each other and create a cluster. So it's like, it's, as it says, it's embedded. So this goes a bit slow.
But it's not only my tech.
Yeah. Okay. It's simple Java only and data co-located with microservice JVM. So the other one is sidecar. In the sidecar pattern, you can use multiple programming languages. Hazelcast supports different programming languages to connect to the Hazelcast cluster. So in this architectural patterns, you have to start two containers inside a pod. One is your microservice, and the other one is Hazelcast member. And with the local network, you just first connect your client to the member, and then it discovers all the other IP addresses and then connects all of them. It's very similar to embedded that I explained in the previous slide. The advantage of this is that as you have two containers, you can define separate memory and CPU requirements. That's one thing, and the data is not shared. So let me, I start hearing myself. Okay.
Is yours muted?
It was muted. I don't know. I was here. So so again, we have two containers here, and we can define memory and CPU requirements per container. And compared to embedded mode, even though they are in the same pod, they can have different CPU and memory requirements. So other than that, all is the same as embedded, and you can use this one too. And the advantage is you can use multiple programming languages. So Java, Node.js, .NET, Python, Golang. Hazelcast has client libraries for all those programming languages. So you can use them. HTTP reverse proxy. This is a bit interesting. This is not available right now, but we are planning to implement such a component in future. So in this pattern, you actually inject a caching into your microservices environment. And your microservices code base, that it doesn't have to know anything about caching API or whatever. You basically cache HTTP responses and put into a Hazelcast cluster. So the beauty of this is that if you implement, for instance, you can implement and you can use company-wide such a product, such a component. The good thing is that you can disable it, the caching, and the other advantage is that your microservice doesn't have to know anything about caching. As far as I see, this service mesh stuff is very popular, etc. So we are checking Envoy service proxy nowadays, and they have a caching abstraction pull request, which is not merged yet. When it's merged, probably we will implement this one, and some other caching products will do the same as well. So that's how you can use caching. So as I explained, you inject the cache. You don't have to change your microservices code, and there's no coupling with any caching API. Client server pattern is the one that we see mostly, because most customers or open source community, they put in production in using this pattern, because you separate microservices layer and cache cluster layer. And in terms of maintainability, that's easier. And that's the main reason. And other than that, the other reasons are, you can use multiple programming languages, and you can implement your microservice. And sometimes Hazelcast is very, very, very fit into Kubernetes. So Hazelcast side, you can also deploy in Kubernetes, but some companies prefer to deploy it in VM. So in this pattern, you can also implement such a. As far as I see, some companies, they just put their stateless workloads on Kubernetes, and all databases, stateful stuff they just keep away and put some VMs. So that Hazelcast works in both cases. And there is a third option that you can use is Hazelcast Cloud. It's fully managed service and pay-as-you-go model. In client server environment, you can just go create an account and start a Hazelcast cluster, and you can connect your microservices into Hazelcast Cloud cluster. So the advantage of this one is that you don't maintain anything, and it's fully maintained and supported by Hazelcast. You just it's just a pay-as-you-go model. So in client server architecture, as I said, cache as a service. So in your architecture, you can create cache as a service and tell every microservice application, etc., to use this cache cluster. Multiple programming languages available, and as I said, microservices layer and caching layer separated. So maintenance are separated. Okay, so I've gone through the Hazelcast use cases and how you can use it in Kubernetes environment. And you decided to use client server. So how can you deploy Hazelcast into Kubernetes environment? So I'm going through some deployment options. So one option is Helm chart. So this command is simply going to install 3-member cluster plus management center into your Kubernetes cluster. And we have Helm chart repository too, but this is also available in official Helm chart repository. So if you do Helm install stable Hazelcast, then you are good to go. You have the cluster and management center, but it has a lot of different configuration parameters. So if you go and check values YAML or see the README file over there, you can do lots of different configurations. One option is that,
Oh, sorry. I was trying to find a good time to interrupt you, but I'm sorry. I have a little Louisville present
okay,
for you.
Thank you
That's
so
for you.
much.
I have to leave. Guys, take the candy, the pizza. Pat's gonna pack up my stuff. Thanks for coming.
Thank you.
See you next month.
Thank you.
Okay, so that's how you deploy Hazelcast into Kubernetes environment. So one interesting stuff is like you can say metrics enabled true. Then Hazelcast starts by exposing all metrics in Prometheus format. So if you deploy Prometheus 2 inside the same Kubernetes cluster, then Prometheus immediately starts scraping Hazelcast metrics, which can be used for instance, horizontal pod autoscaler purposes. And you can change the member counts, configurations. You can pass some other parameters. You can pass CPU and memory requirements, etc. So lots of different stuff you can do. The other option is using Kubernetes operator. With the Kubernetes operator, the difference between Helm chart and Kubernetes operator, you actually extend Kubernetes API, and you can simply, with some REST request, you can create Hazelcast cluster on your Kubernetes cluster. Operator hub.io is some kind of curated operator place, if you haven't heard about it. So Hazelcast is listed there, so you can go and check. Hazelcast also comes with OpenShift for catalog and IBM Cloud private catalog. So if you use those Kubernetes distributions, inside the catalogs, you can find Hazelcast and deploy it. And the third option is Hazelcast Cloud, as I explained. So this is another deployment option. Instead of deploying Hazelcast into your Kubernetes cluster, you can use managed service, and this is pay-as-you-go model. Deployment best practices. So you now know deployment options that you can use, but there are some best practices you need to think about before deploying Hazelcast. So one of them is predictable resource allocation. Predictable resource allocation is actually when you install or deploy something, you need to do your own calculation. What kind of memory, storage, CPU size, etc. So you need to know those details. So for Hazelcast case, you need to define resource requests and resource limits for CPU and memory. So why is that important? It's important because if you don't specify those values, then scheduler might kill your pod in case of resource problems. So Kubernetes scheduler has different quality of services levels, and if you don't define any of those, you are the least lucky one. So you are the first one who is going to be killed. If you are clever enough and then you say that, I don't know if you know about request and the limit concept. Request means that you say, oh, I want to have that much 4 GB memory. And limit, you say that, okay, I wanted to have 4 GB, but I can go up to 16 GB. So that's limit. So some people are clever enough, just they put resource minimum value and then limit to higher value. A scheduler is, you are the next target of scheduler. So it first kills the ones that didn't define anything. But if you give different values, you are the next target. So if you want to have guaranteed placement, then you need to give the same value for request and limit for both CPU and memory. So if it is a 4 GB memory that you need, just give limit and request the same value. So this is predictable resource allocation, and Yeah, it's important for scheduling purposes. The other one is pod anti-affinity. Pod anti-affinity is if you say that you have 3 replicas, you don't know where scheduler will place your pods. Scheduler is the one who is deciding this, and it is very well possible in small clusters you can have multiple pods in the same Kubernetes node. Okay, when I say Kubernetes node, as you know, is a virtual machine underlying infrastructure. As Hazelcast backup count is 1 by default, and if 2 members are located in the same node, and if that node crashes, you lose your cache. When you lose your cache, it costs something to you, because when you lose the cache, you need to reload it from somewhere, from your system of record or data store, etc. So with the pod anti-affinity, you can tell scheduler that don't put two pods in the same Kubernetes node. You can do multiple things with the pod anti-affinity, but that's one thing you can do it. And this is a basic configuration, and it is available in Helm chart values YAML too. So you can enable this and deploy Hazelcast. So the third one is multi-zone deployment with zone-aware. So that's a bit interesting, because Hazelcast is not always preferred to be deployed in a multi-zone environment, because, as I said, network latency is very important for Hazelcast. But in some architectures, they prefer to have more availability. When they do that, they just separate the Hazelcast members in multiple availability zones. And they just think that they prefer availability over performance. But in this picture, normally one availability zone crashes or disappears, it has networking problem, etc. Then on the right side, you will lose 3 members at the same time, which will again cost you some cache loss. But Hazelcast has a feature called partition grouping, and we implemented this in cloud environments and Kubernetes too. So Hazelcast members are aware of where they are located. So they query their availability zone info. And with partition grouping, each member on the right side will send their backup data on the left side members. And all the primary data on the left side, the member 1, 2, 3, will send their backups to the other one. So if one availability zone goes away, then all backups will be available on the other availability zone, and your cluster will just restore all the data. So that's another best practices that you can use. And that's it. So there are some other things that we can talk about, but yeah, those are the things that I put into presentation. But it doesn't end when you do the deployment. So when you do deployment, you just implemented best practices, you selected Helm chart, etc. You know how to deploy it, but then you have some day 2 operations that you need to consider. So one of them is scaling. So when you install Hazelcast, and if you see a load in your traffic, more data is generated, you need to put more data into cluster, you might want to scale out your Hazelcast cluster. And it can be some temporary thing, then afterwards you might just shrink again the cluster afterwards. So you need to do some resizing. So there are some options to do those. So with manual scaling, you just use kubectl scale or Helm upgrade by changing the member counts, and then Hazelcast will add some new pods to the cluster, and then it will start sharing the data partitioning. So you will increase your number of members inside the cluster with a manual operation. So that's one option you can use. For the scaling part, one important stuff is that scale out is okay, but scale in is a bit dangerous because you start killing some numbers. So Hazelcast is using in Helm chart, we are using stateful sets. So the pod scale down is done one by one, and we set by default some higher value for grace periods, and we enabled graceful shutdown. So normal by default Kubernetes grace period is 30 seconds, which means that even if you call this kubectl scale, and if your number of pods will shrink, it will only wait 30 seconds by default. If you don't finish your graceful shutdown in 30 seconds, it will directly kill the pod. So we changed those values in Helm chart and made some intelligent defaults. So you can use it if you use Helm chart instead of your own configuration. Because you can also create your own deployment, stateful set configurations and deploy Hazelcast. So this is manual scaling. The other options are horizontal pod autoscaler. Horizontal pod autoscaler is based on your resource metrics and custom metrics, you can autoscale your cluster. What it means is that for this resource metrics concept in Kubernetes is that Kubernetes is constantly checking your pods and nodes, CPU and memory usage. And you can define a horizontal pod autoscaler based on those values, and then you can create some kind of autoscaler based on some threshold. So horizontal pod autoscaler does that. This is resource metrics. You can also do custom metrics, which is application-specific autoscaler. So normally Kubernetes doesn't know anything about your internals or container internals. But if you expose some metrics and then configure horizontal pod autoscaler custom metrics, then you can do autoscaling based on, for instance, heap size of your JVM inside the Docker container, which is not really available to Kubernetes. So those are the options if you want to go deep. Vertical pod autoscaler is different than horizontal pod autoscaler. Horizontal pod autoscaler will add or remove pods, but vertical pod autoscaler will restart your pods with more or less CPU or memory resources. And cluster autoscaler, yeah, you add more pods, but you need to scale your infrastructure as well. So based on your Kubernetes cluster environment, you might need to enable cluster autoscaler too. For horizontal pod autoscaler, I've written some blog posts last month. So with all the instructions, with custom metrics and resource metrics, you can go and check. I have all the commands that you can play with, so you can go and try it. Rolling upgrade is another day 2 operation. With the rolling upgrade, you might want to upgrade your Hazelcast version. That's one thing. The other thing is you might want to change some config parameters, Hazelcast configuration, or you might want to extend Hazelcast with some additional business logic. Let's say that if you implemented MapStore, MapLoader, and you implemented new version, you need to restart all Hazelcast pods. So those are the reasons you can use rolling upgrade. How you can do it? So Helm upgrade is another option. Again, another option, or kubectl set image is the one you can use. those are the things how you can do it. As I explained, Hazelcast hand chart is using stateful set, and you can also use deployment Kubernetes object, but you need to configure rolling update strategy, because when you do scaling or rolling update, etc., with the deployment, you might end up killing multiple pods at the same time. So you need to do that. And you need to enable graceful shutdown in Hazelcast and optimize grace period. So in rolling upgrade, you need to consider those stuff. Or you can just use Helm chart with Helm upgrade. And the other day-to operation is monitoring. Management center is one option where you can monitor and manage Hazelcast cluster. And the other option is you can use Prometheus plus Grafana. If you start Hazelcast with metrics enabled in the Helm chart, and as I said, we expose every Hazelcast matrix, GMX matrix in Prometheus format. So Prometheus starts scraping them. So you can use for monitoring, and as I said, you can use it for autoscaler purposes too. And the alerting stuff is another thing you need to configure it based on your metrics in Prometheus, or if you use some resource metrics. So those are the stuff that you need to consider. So I'm done with the presentations. I'll just show you how you can do some basic stuff with the Hazelcast Helm chart. So maybe after showing you, then you can ask questions, or you can ask now too. But let me do some stuff. That's dangerous stuff normally. So what I'm going to do is I'm going to install Hazelcast with the Helm chart and with the the basic stuff. So if I go here, let's just shrink this one. So if I watch now kubectl get pods, it's started. Just creating some pods. As I said, when you install Helm chart, Hazelcast with the Helm chart, it will start 3 Hazelcast member and 1 management center, as you see on the screen. Now I am going to check let me check the IP address of the management center. It assigned the public IP address on the management center, and let's go and connect to management center. So I need to create an account, and I need to log in. So as you can see, we have now 3 members. Now let me zoom in a bit. So we have 3 members inside the cluster, and all members, as you see, is running now. So what I am going to do now is I'm going to put some data into Hazelcast cluster. But before doing that, I need to port forward. So kubectl port forward, because I'm connecting from local machine, and yeah, okay. So this is a simple Java code. What it does is that it is creating a Hazelcast client, and it's just putting some dummy JSON file into the cluster, 600. So you can simply divide by 3 because we have 3 members. So when I start this one, then this client is gonna it starts putting some data into. So you can think this part as your microservice, because I don't wanna just create Docker image, deploy, etc. So it started putting some data. And if you go and check over here, okay, and it's created a numbers map, and then it just gives some metrics. If you see here, total number is, it became 600. And we have 3-member cluster. And as you see, it is evenly distributed across 3-member cluster, all the 600 data. And it has 600 backup. Those are also evenly distributed. So if, okay, we put data. So if we delete a pod, what happens? What do you think happens?
The data stays.
That data stays. That's correct, with the 2 members. So let's delete one, but there's gonna be something else too. Let's delete pod Hazelcast. Let's delete the 10. Okay, so we have 3 members, and you see that Hazelcast 0 is killed, but it started immediately by Kubernetes, and it's not ready yet. And if you go and check Management Center, you have 2 members, as you see here, and it's 600 entries. But then it started again another pod, and it joined to the cluster. So this is showing that it's a failover case. So in any case, your pod crashes, you don't lose data, you don't lose cache, and your cluster is recovered.
So the one that you selected had to be the one that had 600 puts to it?
Yeah, but it's only the member got all the puts. As I used, I disabled smart routing just to go through this port forwarding. Normally, as we restarted, you don't see it, but in the previous case, you saw 600 over here, right? Now it's 0 because restarted. It means that all the puts went to that member. But in real microservices environment, with smart client, they will connect to all members, and you will also see those puts evenly distributed too. But that's only for, I just run it from local machine. So let's do it a scale down. So kubectl scale stateful set Hazelcast, and let's say that replicas 2. Okay. See here it started terminating one pod, and you will see that one member will just go away, and you still have 600 entries. I'll do one more stuff. I have a let me show you here. I have a HPA configuration. So in this HPA configuration, I basically say that total CPU utilization is more than 50. You can increase the replica up to 3. I just put it 3 because I need to enter some license key, etc. So we have now 2-member cluster. And if I apply this, kubectl apply resource, so it will create a, and let's watch it over here too, kubectl get HPA. So it created a HPA, horizontal pod autoscaler, based on resource metrics. And see, current target is 50%, but the usage is 20%. I'll do something silly again and do execute some command on one of the pod just to add some CPU load. So yes, there's a yes command. Do you know this? It's basically says yes. It's probably terminal-based questions. It just prints yes. It's like a old-fashioned clicking next button. But when I execute this command, it will just say yes inside this pod, which will add some CPU load. That's not a real load, but yeah, it's just to show the thing. So it is printing inside this yes, inside the pod, and I don't have to keep it too long, I guess. So let me cancel that. You will probably see soon some increase on the CPU usage, and then we will see the Hazelcast 2 member on the left side, if it works. So this is basically how horizontal pod autoscaler works based on resource metrics. Yeah, it didn't work. I can start it again. Yeah, it worked. See, it started a new one, Hazelcast 2. And it is not ready yet. It will be ready. This is still 0 when it starts. I can show you the log too, because that's another way you see how Hazelcast is printing the members in each log. See, it created a 3-member. So you can see each member's IP addresses, etc. So it is ready, and in management center also it is 600 entries with 3 members. So I think that's it pretty much. So we can go more deep and create custom metrics, etc. But as I said, this is available in the blog post, all the instructions, etc. I'll send to James, and then he can share with you too. So I think that's it from my side. There was a Amazon gift card URL on the Meetup webpage. If you just fill in, then you might win some Amazon gift card. Okay. Do you have any questions? I'm sure you have.
I saw like whenever you killed one and another came back, backups. Originally, when I scaled to 2, backups were the inverse of the entries on the other nodes. And then when the third came up, it rebalanced.
Yeah.
And it looked like they fluctuated. And they kind of leveled out. Is that part of what you were talking about? It can be a little network intensive as you're scaling.
Yeah.
Those entries.
Yeah. So this fluctuating is happening, but at the end they just balance, and then every member will have their own primary and backup. So there is a time where this migration is happening, and what we use in health checks, or it doesn't even have to be inside Kubernetes environment. we have some endpoints that you can check if cluster is safe. That's how you need to decide if you can kill one more pod, for instance. Okay? Because when you do in a normal non-Kubernetes environment, if you have 3 members, or let's say 10 members, if you just kill one, you need to wait. If your backup count is 1, you need to wait some time and then start killing another one. And this is exposed via our health check endpoints. There's a cluster safe endpoint. You need to check that one. So there is a time where all this balancing, and also maybe you saw it on the management center too. It just went up to 800 or something. Yeah, if you talk to management center team, it might be considered a feature, or I don't know what it is. It can be considered a bug, but it shows that something is happening, and then it's balanced at the end.
So when that's occurring, just imagining a scenario where you've got these on different nodes within your cluster, and it fluctuates from 600 up to 800. It's probably sending the full set over to the other nodes, and then basically deduping down the only ones it needs.
It might be just the calculation on the management center side too.
I was curious of how much in terms of network you probably would need to plan to make sure you're not oversaturating the pipe.
I mean, it depends on your architecture, and if you do lots of killing, starting, etc., that's all what is happening with the network mostly, because you need to redistribute all the data, and depending on your data size, it can be painful. So what we do is not a normal day activity. It's just failover cases. But if you have highly unstable networking environment, then I don't know, you need to calculate your partition counts, your data sizes that you put inside each distributed map. You need to do your own calculation. But there are lots of instabilities, then that's a problem. Another problem we just see and try to solve also split brain problems. So if you have networking issues, then you might end up having multiple clusters, 2 clusters, and they think that they are the real cluster. And we have some kind of merge policies where you can apply, or you can even implement your own merge policy. So you can't assume network is always there and it's gonna work. So we have things that you can use to fix such a problems or prevent the problems. Yeah, failure is normal. Not everyone is just getting this. Not only network, failure is normal thing, and then you need to calculate your SLA, SLO, whatever, all the stuff. Thinking that failure is normal, it can happen. What you can do when failure happens, that's the thing you need to decide. Any other question?
I have more.
Yeah, okay. We can go and drink something. If you don't have questions, so then thank you so much for joining me. I enjoyed. I hope you enjoyed too. And yeah, luckily it worked. Yeah, that's
Here's kind of a general question. I was just wondering, how long has this been out in the market, and what kind of companies are using this? You know,
Okay.
Specific, but if you can, that would be nice too.
okay. Let me close that one. Are we still recording or?
Yeah.
Okay. So the question was.
I was wondering what kind of companies are using this, and how long this has been out.
So Hazelcast is open source, and it is, I guess, 11 years old. It's not something new. We have lots of customers in Fortune 50, and we just recently raised $20 million too, just to expand more customers. Actually, inside the customers, but those are sales guys. They know much about it. we are healthy startup. I mean, we have very big names.
Yeah, okay, that's good. I've just never heard of it before.
Yeah, the thing is that it is mostly maybe focused on Java ecosystem mostly. Maybe, I don't know. Maybe that's why you don't hear. Okay, thank you guys.
Thanks for coming, man.